Concept 22, inverse functions. Let's start with some vocabulary definitions and formulas. This is just a review definition. Function. In math, a function is a math relation, which is a pairing where each input has exactly one output. So each input has exactly one output. Now this is the new concept, inverse functions. These are functions that undo each other. In math, we have inverse operations, like addition and subtraction. They undo each other. Multiplication and division undo each other. Well, these are full functions that will undo each other. And what that means is that the input and the output of one function are the output and the input of the inverse function. So let's take some notes. First of all, to find the inverse of a relation, which is a pairing in math, and this relation is made up of ordered pairs, you simply switch the inputs and the outputs, or the x's and y's. So we've got here a relation of these pairings. -4, -2, -1, 1, 3, 3, and 5, 4. So the inverse would be, we just switch that. So now our input becomes -2 and our output becomes -4. Input is 1, output's -1, input is 3, output is 3, input is 4, output is 4. Now let's graph these sets, and I'm going to graph them in different colors. So the original function, I'm just going to graph these points in blue. So it's the point -4, -2, -1, 1, 3, 3, and then 5, 4. And then after I graph this set, I want to show you something interesting about the graphs of a function and its inverse. So we'll start with -2, -4, 1, -1, and right away you could start to see maybe a pattern between the blue and the red points. 3, 3, so these get graphed right on top of each other, and then the point 4, 5. Now let me draw one more thing. So I'm going to put a diagonal line right down the middle of this graph space. We could write the equation for this diagonal line. It's simply where y equals x. So when you graph a function and its inverse together, the graphs are reflections across the line y equals x. And then just one final note, that when you have an original function, its inverse, you just reverse the inputs and the outputs. So the input of the original function becomes the output of the inverse. Next, let's look at how to identify if a relation that's in ordered pairs, or maybe it's an equation form, is a function. So this is just a review. And then remember that if a relation is a function, that each input has only one output. So if your relation is in ordered pairs, one easy way is just to make sure that no x's are repeated. If you see an x that's repeated, that means that that input has two outputs, and so it's not a function. A second way is if you're looking at a graph of a relation, you can see if it's a function if it passes the vertical line test. That means when you pass a vertical line anywhere through the function, it will only intersect once. If it intersects the graph more than once, then that graph is not a function. And then finally, for equations, you can think in terms of 1 or 2. So you can imagine any inputs where you would get two outputs. In that case, your equation would not be a function. Or you can imagine or graph the equation. and see if the graph passes the vertical line test. So let's start with A. So A, we've got a relation that is a collection of ordered pairs. So I'm looking at my inputs. I've got 3, 2, 1, 3. So I have a repeated input. So that input of 3 has two outputs, 4 and negative 2. So this does not fit the definition of a function. On B, I look at that and I realize that that is in slope-intercept form, and it's the equation of a line. So if I quickly plot this line, you don't have to actually plot them each time. You can just picture, whoops, try that again. You can just picture lines, and you know that if you pass vertical lines through this graph, it will only intersect once. And so it does pass the test. An equation of a line is a function. Now finally, we've got this square root function, and you'll notice right here, plus or minus. So what that means is that when we put in an output or an input, for example, let's put in 9 for x, it tells us that we need to take the positive and the negative square root. So if we take the positive square root of 9, that's 3. 3 minus 3 is 0. If we take the negative square root, that's negative 3, minus 3 more is negative 6. So right away, this one input of 9 has two outputs. So we can tell that this is not a function. So we found inverse of a relation when it was listed as ordered pairs, but here are the steps if you have a relation in equation form. So these are the steps to find the inverse of that function. The first thing you want to do is to interchange the inputs and the outputs, the x's and the y's. Then you're going to solve the equation for y, and then finally replace the y with this notation, which reads the inverse function of x, to show that the equation is the inverse of the original. And then it says determine if both the original equation and its inverse are functions by using the test of their graphs that we just talked about in the example just before. So in A, we've got f of x equals 3x minus 1. Hopefully you recognize that as a linear function. So we know right off the bat that a linear function is, or it is in fact a function, passes the function test. So let's write that in equation form. And now what we're going to do is we're simply going to switch the x and the y. So wherever I see y, that becomes x in my equation. And then where I see x, that becomes y. And that's because with an inverse, our inputs and our outputs are reversed. So now I'm going to solve for y. So I'll add my 1 and then divide by 3. So I'm just going to write my y first. So y will equal 1/3 x minus 1/3. And then the last thing is I'm going to use that inverse function notation to replace the y so that I know that this is definitely the inverse of my original. What that means is that this function will undo that top function. Now, I already know that my original is a function because it's in a line, and I look at my inverse and I can recognize that as a linear equation as well. So both are functions. That means for each input that we would put into either of these equations, we only have one output. Let's try B now. So hopefully you recognize that as a quadratic and it will graph as a parabola. So let's put it into equation form and then we'll go through those steps again to write its inverse. So we have y equals, in parentheses, x plus 2 squared. I'm going to interchange my x and my y, which is interchanging my inputs and my outputs. And then I'm going to solve for y. So the first thing I want to do is to take the square root. Now, when you're solving and you impose a square root to solve, you need to put the plus or the minus in front. Because when we solve, we consider both cases. And then we'll subtract the 2 from both sides. I'm going to put my y on the left side of my equal sign, equals, and then I'll have plus or minus the square root of x, and then minus 2. It does not go underneath the sign, it goes out to the side. And then last thing is I'm just going to replace my y with that function notation, inverse function notation. So now I can see that this is my inverse function that will undo that original. So now to tell whether these are are functions with the original, I'm going to think about the graph, okay? And I know that this is going to be a parabola that opens up and is going to have its vertex at 0, -2. So that's a very rough sketch. If I think about the vertical line test, passing vertical lines, it will definitely pass. So I'm going to say, yes, this is a function. Now, with my inverse function, I'm going to think about the equation. And like we did in an earlier example, if I were to put in 9 as an input, this is telling me I need to take both the positive and the negative square root of 9. So that would be positive 3 minus 2 is 1. The negative square root of 9 is negative 3 minus 2 is negative 5. So right away I can see that this does not fit the definition of a function. So I would have to say that no, it is an inverse. It is the inverse of my original, but it just doesn't end up being a function. Now here are some features of inverses that will help you when you work with them. Inverse functions have points that are reversals. So we've talked about that, but that means the input of one is the output of the other. So if you have, for example, the point 3, 2 in your original function, then 2, 3 will be a point on the inverse. So you can use that fact to help you graph functions and its inverse. Another feature is that inverse functions have domain and ranges that are reversals. So if the original function has a domain and range of x is greater than or equal to 3 and y is greater than or equal to 0, that means the inverse has the domain and range which are reversals. So x will be greater than or equal to 0 and y will be greater than or equal to 3 for the domain and range. So let's use those features to help us graph the relation and its inverse. And I'm going to start with the original graphing in blue. So since I can recognize this as a linear equation, my first point goes at 3, and then I'm going to go up 2 and over 1, and I'm just going to draw that line. And I'm going to write down what points it'll let me. Okay, so I graphed the point 0, 3, and then after following my slope, I graphed the point 1, 5. So in red, I'm going to write my inverse points. So that'll be 3, 0, and 5, 1. So 3, 0, and 5, 1. And now I'm going to graph this. Just going to do a couple more points so I get it right. There we go. And then also, if you can remember earlier how we talked about that the graph of a function and its inverse will be symmetrical over this diagonal line, and so I'll put that in. You can see that that's true. Now in the next one, we've got a quadratic equation, which hopefully you'll recognize or remember that it'll graph in a U-shaped curve, a parabola. So we can start with the points that we know from when the way this graph is transformed. So thinking back to earlier units, we know that this is going to move the graph 3 to the right off of the origin, 0, 0. So its vertex is going to be at the point 3, 0. And then if I plug in x values just to the left of that, so I can plug in 2. 2 minus 3 is negative 1 squared is 1. And then plug in not 3, sorry, 4. 4 minus 3, 1 squared is 1. I have enough points to graph that parabola. Now we'll use the feature of the inverse just having point reversal. So for the inverse we can graph the points 0, 3, 1, 2, and 1, 4. And I've got another U-shaped curve, but this one's on its side. So we can use the graphs to help us see whether there are functions. Remember that vertical line test. So now I'm looking at the blue graph and I'm imagining vertical lines through it. They will only pass through that parabola once at any given point. So that is, yes, a function. Now the inverse, if you look, it's going to pass through twice every time. So the inverse is not a function. On this next one, let's find the inverse of this function. So we'll put it in equation form. Y equals, oh, I'm in red, cube root of x minus 5. So the first thing I'll do is just interchange my x's and y's, just those steps to find an inverse, and then I'm going to solve for y. So I can start by cubing each side. I get y minus 5, add 5 to both sides, so x cubed plus 5. And for the last problem in the notes, we're going to look at a real-life problem. When you find inverse functions of real-life problems where we're not using the x and the y variable, we do not interchange those variables because of the meaning that's attached to them. You just solve for the other variable to find the inverse function. So when the directions say find the inverse of the formula to convert Celsius to Fahrenheit, so Fahrenheit equals 9/5 times Celsius plus 32. We don't interchange the x and the y, we just solve for Celsius. So I'm going to subtract my 32 from both sides and then multiply both sides by 5/9. So 5/9 Fahrenheit minus 32 equals Celsius. So this is my inverse function. And now I can use that function to find the Celsius temperature that corresponds to 35 degrees. Whoop. So instead of Fahrenheit, I'm going to plug in 35. So 5/9 times 3, which is 15/9, or 1 6/9 2/3 degrees Celsius. So just a last note is in real life problems, do not interchange the variables when you find the inverse. You simply solve for the other variable, and once you've done that, what you've got is the inverse function. Now you need to do the independent practice problems. I'm not going to check them on the video, so you do them on your own. Look back at your notes to help you. And then when you do your teacher talk right after that, go over these problems with your teacher to make sure that you understand the concepts and the processes.